Good afternoon. Uh, I'm Jim Johnson. I'm going to be your presenter this afternoon. Get this started here. We're going to talk about salts, where they come from, what they are, uh, how they cause corrosion, how they cause coating failure, and then we're going to talk a little bit about allowable levels. So let's get started. There's corrosion caused by salts, just to give you an example to show that it is something worth considering. When this surface was tested, all this corrosion you see was caused by nitrates, substance not often looked for, but it's pretty prevalent as being out there in the field. This corroded surface here was a bridge that was painted 18 to 24 months before this photo was taken. It's a comparatively new coating. This one was caused by primarily chlorides, though it does have some sulfates and some nitrates showed up. This photograph, this is a coal jetty where they load and unload coal off of barges and ships. All this failure here, failure analysis was done, and virtually all of this is due to sulfates. So we're looking at corrosion caused by chlorides, sulfates, and nitrates. That's typically what we encounter. Just to show you what a difference it can make, this is a bridge in New York City. At the time this was painted, 4 to 5 years previously, notice the beams here are in relatively good shape. After 4 to 5 years of history, this piece across here that supports the roadway, it's got an expansion joint right over the top. Of course, those expansion joints virtually always leak, so you got a source of de-icing salts there. Quite often they salt this thing. Those salts came down there. At the time this was coated, nobody tested for or remediated salts. They just coated right over them. So you see the difference of a 5-year-old surface coated over salts versus a 5-year-old surface that wasn't coated over salts. What are salts? First off, there's a difference between soluble salts and insoluble salts. We'll get into a little bit more of the difference after a bit, but we're primarily concerned over soluble salts. The ones we commonly encounter out in the field are chloride, sulfates, and nitrates. There are other ones like iodides, bromides, and fluorides. Though they're fairly common, quite a few of the cities add fluoride to the municipal water, supposedly to stop tooth decay. It actually does quite well at decaying steel. Practically nobody ever tests for fluoride contamination, probably because there is not a field test kit available. You have to take a sample off the surface, take it into a lab for analysis. So it's probably not commonly done because we don't have the kits available, and they don't cause near the problem as the chlorides, sulfates, and nitrates because they're not as common. When we first started detecting that salts were bad 50, 60 years ago, the only thing we could really do was test conductivity. We didn't have the means available to identify the various salt ions. So they started conductivity testing as 50, 60, 70 years ago, somewhat outdated now, but basically they consider a salt anything that adds conductivity to water. It can be minerals, it can be metals, it can literally be bacteria. It can be dead bacteria. They add conductivity to water, it's a salt. They aren't necessarily all detrimental. They are termed as ionic contaminants. They're water-soluble inorganic compounds. Like we say, they're soluble salts. Insoluble salts are different. All the NACE and SSPC documents, they all term them all as non-visible contaminants. Salts are broken down into two categories. Loose salts, that's salt that's lying loosely upon the surface, or salts that have formed an electrochemical bond to the metal surface. The chloride is bonded. What we typically encounter in salts is sodium chloride. The chloride is bonded to the sodium. It really prefers steel. It likes zinc even better. But what the chloride ion will do is disassociate from the sodium, bond to the steel. It forms an electrochemical bond. And when we go in to remove the chloride ion off of steel, we've got to break that bond. And the longer that salt's been on there, the more tightly bonded it is. So we have salts that have been electrochemically bonded and loose salts that are lying on the surface. Loose salts, you can typically wash them off with a garden hose. Pressure washer, no big deal. They're just lying loose on the surface. Sources of salts. We've always known that salts come from marine bodies. We think they go in a half-hour mile or a mile from the coast. We'll have a map show you differently here in a bit. De-icing salts, primarily sodium chloride. The industry is getting more into magnesium chloride. You hear them talk all the time about mag chloride de-icing salts. It's just a different combination of species on what the chloride is bonded to, whether it's bonded to magnesium or whether it's bonded to sodium. Either way, it's still the chloride that's doing the de-icing. Chemical processes. Chlorine and sulfuric acid are the two most widely manufactured, widely consumed, and used chemicals in the world. All kinds of chemical processing requires chlorine. Everything from laundry soap to battery acid. Battery acid, by the way, is sulfuric acid. So they're widely used chemicals all over the world. We'll typically find more from chemical processes in the urban areas than in the rural. Acid rain. Chlorides, sulfates, and nitrates occurring from all these different places. They get into the air. The air picks them up, transports it long distances. The rain falls out of the clouds. It picks up those chemicals coming down through the air, comes down as acid rain on the surface. Everybody's pretty well aware of that. You look at new vehicles transported on trucks or on trains. They've got plastic over the fenders, over the hoods, protecting that finish on that new vehicle, because if they found out the acid rain was strong enough, it actually would etch the new paint. If it's a strong enough acid to etch the new paint, it's certainly strong enough to corrode steel. Fossil fuel power plants. They keep talking about the coal-fired power plants dirtying up the air. All fossil fuel, whether it be coal or whether it be oil, has got sulfur and nitrogen in it. When the coal is burned, what it releases up into the air is sulfates and nitrates. In the refining process, the sulfur is typically taken out of the oil, of the crude oil, so is the nitrates. So we don't get it much in automotive fuel, but we do end up with some other things. Diesel fuel, we will have sulfates. Even though we have low sulfur fuel, we typically don't have no sulfur fuel. Vehicle emissions. If you listen to the news at night, they talk about automotive pollution. They talk about what's coming out of the tailpipe is NOx, or nitrous oxide. The nitrous oxide from burning unleaded gasoline, what's left after the catalytic converter, is nitrous oxide, comes out the tailpipe, mixes with the oxygen and humidity in the air, and comes down as nitric acid in acid rain. When that acid rain hits the surface, the H2O evaporates and leaves the nitrates behind. If it's emissions from a coal-fired power plant, it's primarily sulfates. They mix with the oxygen and the humidity in the air, come down as sulfuric acid. The H2O evaporates and leaves the sulfates behind. Water and wastewater treatment. Between the city water treatment plants are typically adding chlorine to control bacterial growth in the freshwater system. In the wastewater treatment, they're using all kinds of chlorine. They're using sulfuric acid. Other things like cooling towers and swimming pools, they add sulfuric acid to balance the pH. So you get a lot of that coming into the wastewater treatment systems. Abrasives. As it relates to seal surfaces, if you got an abrasive that's contaminated with chloride or sulfate, you get above a certain level, and when you abrasive blast with it, it will transfer onto a clean, uncontaminated steel surface. It may be a very low level, it may be below the allowable level, but anytime you get contamination on a clean surface, it's very hard to get that surface back to a totally non-contaminated level to get the most lifespan as possible out of a coating. So even if you're adding only a little bit of contamination, it's still impacting the overall performance over a 20-year period. These are charts of the United States. These charts are in kilograms per hectare. In the coatings industry, we primarily look at micrograms per square centimeter. It isn't exactly totally 100% accurate, but it is very, very close. If you take the level in kilograms per hectare, move it 1 decimal point to the right, and that'll be the micrograms per square centimeter. Right down there at the southern tip of Illinois, it shows the chlorides as 26. It's actually 260 micrograms per square centimeter. We talked about, I mentioned just a little bit ago about the chlorides coming in off the coast. You can see here down on this map off the Gulf of Mexico, these winds predominantly out of the south come over the Gulf, come up over Louisiana, Mississippi. It carries those sea salts 200 miles. It's amazing. It takes them all the way up into Arkansas. It does take them well over 100 miles inland. Same thing up here off Seattle. Seattle, Portland, those prevailing winds off the ocean carry those salts in close to 100 miles. It's kind of easy to see a geographical patterns here. Down in the California area, the prevailing winds are coming off the shore and blowing out to sea. It's where they have all the grass fires and everything. They've also got beautiful weather. Now, that damp weather off the ocean is seldom ever carried inland. The predominant winds are seaward. So you can look along most all of our coast. You can see just how far inland that salt blows. That's the amount of chloride just naturally deposited out of the air in 1 year. So again, we look at southern Illinois, right where the Ohio River meets the Mississippi River. See, we got 260 micrograms per year, and what we're looking at allowable levels is more down in a neighborhood of 3 to 5 to 7. So though the rainwater washes off a lot of it, there's also a lot available. Sulfate ions. Same thing, move the decimal place one place to the right. You can see the higher sulfate levels all down the Ohio River Valley with all the coal-fired power plants down here into Tennessee, into Kentucky, Illinois, Indiana, Ohio. A bunch of coal-fired power plants over here. So you can very well see where we've got the highest sulfate contamination. But notice over in the western states, out here in Idaho, up towards Boise, Idaho, we still have 30 micrograms per year. Over here in central Montana, we've still got 10 micrograms per year. So as you look at each one of these maps, you will see there's not a single place in the entire United States we don't encounter chlorides, sulfates, and nitrates. So it isn't a matter of you only have to test if you're near a marine shore. You don't have to only test if you're in what they call the Rust Belt. You're going to have contaminants nationwide every place you go. Nitrates, right there at the Ohio and Mississippi mouth, we got 120 micrograms per year. Again, a lot of these nitrates come from burning coal in those coal-fired power plants, so you can see how corrosive that is. Talk about acid rain. Normal rain is a pH of about 6. You can look at these maps and see the pH in the most highly contaminated areas is actually down 4.7, 4.8, 4.9, really quite low. But even in the good areas, there's very few that are 6 or above. 5.6, 5.7, there's a 6.1. Even out here in the Rocky Mountain states, they're down below 6. It's primarily not something that was caused locally, but it's brought in on the winds and the travel of the air. So we have acid rain conditions pretty well across the whole entire country. Typical power plant stack, putting off several million tons of sulfates and nitrates per year. Where they'd be putting off 1 million tons, we're measuring sulfates and nitrates in micrograms, 10,000th of a gram. So where we're measuring in such minute amounts, they're putting it out tons and tons and tons. By the way, they have cleaned up their act considerably. Those latest maps are from 2009. If you go back to 2005, 2002, 1999, you can see those maps were much, much more heavily polluted. Every year, without all this radical stuff, they have still managed to clean up their act every year just by the old clean air standards. They had a standard they were supposed to get down to by 2020, and we actually achieved those standards in 2012. So as much as people might complain about dirty air, we're already ahead of what we're supposed to, the cleanup they were given until 2020 to do. Effects of salts. They cause corrosion. They cause osmotic blistering of coatings. They interfere with the adhesion of coatings. There's some steel plates. They were abrasive blasted pretty much to white metal. They were left 24 hours just at ambient humidity. You can see 24 hours later, over here on the left-hand one, this little spot, if you actually looked at the original coupon that they photographed, this is a fingerprint. somebody picked that panel up and they touched it with their thumb, and just the salts from their touching it was enough to have rust 24 hours later. And as a NACE certified level 3 coating inspector, if I were to look at this previous slide, somebody told me to test that for salts, I wouldn't have tested up in this corner or down along here someplace. I'd have tested right here smack in the middle. I figured that was typical of the entire piece of metal. You look at it 24 hours later, this is rusted back here. We've got a heavier rust back here. We've got much more rust back here. Really points out an example that where you test for salts, it can be much, much different, just a matter of inches away. Just inches away, you can have nothing here in the middle. You could have 20 or 30 micrograms up over in this corner over here, or 10 over here, or whatever. I'm not attempting to put a numerical value on it, just an example. You see this one, how heavily rusted it is? If you look at the previous picture, you can actually see all those pits in there. So you see pitted steel that they blasted, and it starts rusting back like this in practically no time. That's just an example that it's highly contaminated. Corrosion cell. The corrosion cell consists of 4 components. You have the cathode, which is provided by the steel itself. You have the anode, provided by the steel itself. You got the metallic pathway. Steel is made up of a granular structure. If you look at that steel under magnification, there are smaller and larger granules of steel. Well, the size of the granules, the larger and smaller ones, they are cathodic and anodic to each other. Yet they're connected by the metallic pathway. The 4th component that's missing is an electrolyte. Electrolyte is a liquid that conducts electricity. So if you have salt plus moisture, or pure H2O, you have a substance that will conduct electricity, and that's called an electrolyte. It requires those 4 components. There's a battery, which is actually a corrosion cell. We've got the anode, which corrodes. We've got the cathode, which does not corrode, that the anode is protecting. They're connected through a metallic pathway, and we've got the electrolyte. Now that light bulb is part of the metallic pathway. If you shut the switch off and shut the bulb off, or if you took it out of the socket, you would no longer have the 4 components, because that metallic pathway would no longer be continuous. It would be broken when you took that light bulb out of it. Same thing in this battery. If you allowed the battery acid to get down below the plates so it didn't make contact with both plates, that light bulb would go off. You'd break the circuit because we didn't have the electrolyte. So you've got to have all 4 components to get this activity to occur. Yeah, it corrodes the anodes here. It comes down through here, carries back down through here. Just goes. A battery is just an electrical circuit, and corrosion is just an electrical circuit. Salts are hygroscopic. They draw moisture. A lot of housewives you see in the salt shaker on the kitchen table, they'll put grains of rice or pieces of soda crackers or these little oyster crackers in there to absorb the moisture. If they don't, the salt will absorb the moisture right out of the air, and it'll cake up and get hard in the salt shaker. So salts do draw moisture. All liquid applied coatings are moisture vapor permeable. and the salts will draw the moisture vapor through the coating. They don't actually draw a droplet of water through there. They actually take the moisture vapor and suck it right through the coating, where it condenses or coagulates back into moisture behind the paint film. When you take that pure H2O, combine it with a salt behind the coating, like a chloride or a sulfate, it will make hydrochloric acid or sulfuric acid, and that will carry on corrosion quite nicely beneath the paint film, which will cause a blister in the coating. It'll cause the coating to fail, but long before the coating fails, the corrosion action is going on beneath the coating. Some coatings are less permeable than others. A standard epoxy versus a glass flake filled epoxy, the glass filled epoxy is much less permeable because even moisture vapor coming through the epoxy is going to have a long circuitous route to go around those glass platelets. They have to work around them, kind of like going through a maze. A 1/4-inch trowel down is much harder to get through than a 10 mil coating. So some coatings or coating systems are less permeable than others. All the paints aren't equal. It's an example of hygroscopic action there. This beam was painted, wasn't even a year old, and you see where the moisture under the underside of the bridge is sucking moisture. The salts are sucking moisture right through the paint, drawing it through, setting up a corrosion activity beneath the paint film. The paint has not yet failed. That's rust bleed starting to come out through the paint, but the active corrosion is going on beneath the paint, behind it. Osmotic blisters. The same hygroscopic action which causes corrosion also causes osmotic blisters. Just because that salt has drawn moisture through the coating doesn't mean it quits. That salt will keep drawing until it reaches what it considers an equilibrium. So those salts will continue to draw, and as they draw, they build up pressure. The average industrial coating has got a bond strength of about 600 to 900 psi. Yes, there are various coatings that have got a 3,500 to a 5,000 psi bond strength, but that isn't what we normally encounter in most of our work. Excuse me. But what we typically encounter in most of our work in tank landings, bridges, and everything, typically is in the 600 to 900 psi bond strength range. Now I haven't been able to verify the accuracy of these numbers with this PSI. Still searching for the original research work that came up with the numbers, but as a general rule, they're pretty close. Sodium chloride, 2,200 psi. Well, if the coating on top of it has got a bond strength of 900 psi, you can see how it easily lifts that coating, and as it builds up pressure, it keeps lifting it and tearing it loose from the first surface, and the blister gets bigger and bigger. Ferrous chloride, that's where that chloride ion has left the sodium. It's disassociated from the sodium, formed an electrochemical bond to the steel, and become a ferrous chloride. Now, notice we got a Cl2. Now it's up to 3,700 psi pressure. So again, the 900 psi coating that's on there, you're building up more pressure than the bond strength of the coating, so the coating's just going to lift. Zinc chloride, 22,000. That's just shows you how super aggressive a zinc chloride is. Zinc and chloride is a very aggressive situation. Just a standard example of what you typically run into with osmotic blistering caused by salts. If you look at these blisters on this center pole, you'll notice there's a big one here and a small one here. You see they're smaller and bigger. They vary in size and they're sporadic. You've got a cluster of blisters here. You've got an unblistered area there. Then you've got more blisters again. It's real indicative of blisters caused by salts that they are sporadically dispersed and they vary in size. That's very, very common. You know, if you've got solvent entrapment, usually it's because they either use the wrong solvent or they used too much of it. First off, it's mixed evenly throughout the paint, so the blisters are usually pretty evenly sized and pretty evenly spaced. And when you break the blisters, it'll smell like solvent. You can send it into the lab and they can analyze it, and it'll analyze as solvent. You break these blisters, these here, it'll feel like water, it'll smell like water, it'll taste like water. Send it into the lab, they'll tell you it's water. They're pretty easy to tell the difference between osmotic blistering caused by salt, blistering caused by solvent entrapment, and blistering caused. The third method that's commonly encountered is blistering from a cathodic protection system that's overdriven. It's had too much power applied to it, and when that excess power is applied to the surface of the steel, it causes little bitty blisters. They're very similar to goosebumps on your arm. They're very evenly sized, very evenly shaped. You run your hand across the surface of the steel inside of a tank that's had an overdriven CP system, and it's like running your hand down your arm when you got goosebumps. That kind of like sandpaper, all the same size and same continuity all the way through the whole thing. Adhesion. High salt levels can act much like dust in not allowing an intimate contact with the substrate or to the intermediate coat. Well, we had a project down in the Florida Keys. It was a lighthouse down there. The engineer writing the specs was well versed on the fact that the salt-laden air had come in at night and contaminated a surface. He knew the lighthouse was contaminated, so he required it to be washed down with our salt remover, remove the salts. So they did that. They pressure washed the lighthouse, got the salts off of it. They dried it up. They applied the primer coat, went home for the night, came back the next day and applied the intermediate coat, went home, came back the next day and put on the top coat. Several months later, the intermediate coat was pulling loose from the primer, and the top coat was coming loose from the intermediate coat. Well, when they did an analysis on it, they found that just by leaving that surface overnight in that salt-laden air, it contaminated that surface with enough salt that the next coat could not get a good bond. So they do interfere with adhesion, and it can be from just overnight. And you don't have to be in the Florida Keys. All you have to do is be downwind from a cooling tower. You see that when in the cooler temperatures, you see the steam coming off these cooling towers. That's basically little water droplets in the air. And those water droplets come out of that cooling tower, which is loaded with chloride and sulfate. Because they circulate the water to cool it down, and they evaporate it to cause a chilling temperature drop, they keep recirculating that same water, and it's warm, so bacteria grows quite freely, so they add chlorine to it as a biocide. And they keep adding more chlorine to it. And as the bacteria is killed off, it drives the pH up, so then they add sulfuric acid to bring the pH down, to balance the pH, to keep it from scaling up. So they're continually adding chlorine and continually adding sulfuric acid, and very seldom do they ever actually just dump the cooling tower and start with fresh water. They run most of them pretty much run a constant bleed, where they get to a certain level of conductivity, it opens up the bleed valve, some dirty water comes out, some fresh water comes in, and they add more chemicals. So all you have to do is be in the drift of one of those cooling towers. I've seen it happen a half a mile away. Visually clean substrates are not adequate. You know, for 30 years, we had nothing but visual standards. More than that, 40 or 50 years. We worked by white metal, near white, commercial blast. They're all visible standards. Soluble salts require testing to be detected because they're non-visible. So we've moved from the visible world to the non-visible world. So we do have to do testing to find out if salts are even present. And then the question is, which salt is the problem? It's primarily dependent on the service environment. Consider possible sources: roadways, power plants, cooling towers. You look at the things around you and look for a half a mile away in the direction of the prevailing winds and see where, if you've got a coal-fired power plant, do you have a water treatment plant? Have you got a cooling tower? Have you got a big industrial complex where they're using a lot of chemicals? There are numerous sources, so you always have to consider the sources. But when you are not sure, always test for the other salts. Testing is always less costly than a coating failure. Coating failures are unbelievably costly. They cost time and time again. We've tracked cost and found that to go in and redo a job is 5 or 6 times the cost per square foot of when you did it the first time. Actually, it's more than that. Which salts? Typically chlorides, sulfates, nitrates, and special site considerations. If you're in where they're adding chemicals to water, see what chemicals there are. It could be an iodide. It could be a bromide. It could be all kinds of things. So when you get on a particular project or site, ask about other chemical exposures. Where do you test? Typically, you test at the locations of corrosion. You typically test where the coatings have failed. If you've got a surface that 60% of the coating is in perfectly fine shape, it's only 40% that's failed. If that coating has got a couple of years lifespan and it hasn't failed, wherever the non-failed areas are, chances are there's little to no salt beneath it, or it would have failed. So don't ever waste time testing areas where the coating was good. Always test where the coatings have failed. And also test at weld seams. Look at, there's a picture. Weld seams. You see the weld on the weld seam in that roof of that tank. We encountered a tank that was having problems with corrosion at the weld seams. Won't go into a long story, but the owner of the tank come back and said, "You guys have done a lot of tank lining for us. They've always done fine. This particular tank, not one that we had coated, but that particular tank was failing, so they wanted us to find out why." Well, we went in and blasted the weld seam, and we blasted 6 inches on either side, so a foot wide, down the length of the weld seam. And when we measured even just an inch or two away from the weld seam, we got 0 salts, 0 chlorides. When we tested right smack on top of the rusted weld seam, then we were picking up chlorides. So, and it was not just like a handprint, like some worker put his hand there, brace himself for something, or get salt from his skin on it, but in a solid, I mean, that's a pretty solid mass of failed area there. So it wasn't like a fingerprint or two. We went back and talked to the welding rod manufacturer about what they had used for rod in there, and they wouldn't tell us what the metallic content was. That's private information, but they would tell us that the flux that's on the outside of the rod, they use the flux to make it weld smoother. One of the components of that welding flux was a wood fiber. And it turns out that wood fiber was bleached at the pulp mill, and then it was incorporated into the flux on the rod to make it burn nice and smooth. Well, what was happening is as they would burn that weld, that wood fiber itself would burned up, but it left that chloride residue behind. And we did some further checking into the industry and found out that about 60 or 70% of the commonly used stick welding rod has that wood fiber filler in the flux. So if you see rust on the weld seams, test right on the weld seams, because that may have been done by welding rod that had that same wood fiber filler in it. This particular photo, I use it as an example of where to test. You know, if I were a specifier or an inspector and I wanted to find any contaminated surfaces, I would look at areas where the coating had failed. I would look down here where there's areas of corrosion. I wouldn't bother testing right here. That's good, sound, intact coating. If there were any salts behind it, it would have failed. So just the fact that it's sound, intact coating tells me that the salt levels there aren't of a concern. But we run into some of these contractors that if they got a project that doesn't pay extra for salt removal, they just got to put in a flat dollar bid, salt removal included. They don't want to find salts. Well, they've gotten pretty handy at coming to know that if they test over here and test over here and test over here, they aren't going to find salt, so that's where they want to test, because they don't want to spend the money doing salt removal. So depending on who you are and what your interest is, the asset owners, they, of course, want the best job. Usually the inspector does too. The specification is going to usually tell you where to test, but sometimes it doesn't. When it doesn't, if you want to stop a failure, watch the test at the areas of corrosion, at the areas of coating failure, and at the weld seams. Let's talk just a little bit about flash rust. Flash rust is a visible indication of non-visible contamination. All that's telling you is that salts were there, it corroded, and now it's rusting. Truly clean, uncontaminated steel will not rust even in 100% humidity for thousands of hours. And that's a quote from Dr. Gerald Salts. He did a lot of research for the NTSB, the shipbuilding program, and he found in his testing, both in the lab and in the field, clean, uncontaminated steel will not rust even at 100% humidity for thousands of hours. And I have actually seen that the same way myself. So if you've got flash rust, it's because you've got contaminants on the surface. And many of these specs, even though they allowed 3 micrograms of chloride, you can have a half of microgram or 1 microgram of chloride can cause a lot of flash rust. Heavy flash rust or flash rusting very quickly is an indication of contaminant. You know, if you got a nice, smooth, even light reddish brown and then a heavy dark brown area. That heavy dark brown area is an indication of an area that's got heavy contamination. Probably go back and test it. You may have to decontaminate it. Even real low salt levels cause some flash rust. Just because you're down to 3 micrograms is approved for a tank lining doesn't mean that isn't going to have flash rust anyway. So if you have 3 micrograms of chloride that meets the specification, and the spec also says that it shall not have any flash rust, if you're going to leave that surface over any amount of time, you're either going to have to brush blast the flash off of it or use some kind of a deterrent to keep it from happening. It's a good example. That's a steel beam on a bridge. It was in full containment. They went in at 8 o'clock in the morning and blasted this bridge beam. They were blasting in that containment all day. When they quit for lunch at noon, they came out of the contaminant. The air cleared up a little bit, and I went in there and took a look at it. This is the result between 8 o'clock and noon. This is 4 hours. And every place you see this heavy rust bloom, those are all contaminated areas. This clean, bare white metal down here with no rust on it at all, there's no contamination there. You could probably leave that bare for a week and it won't flash rust. But these areas here, that's a visible indicator that you have non-visible contaminants. That just lets you know instantly you've got contamination at those locations. There's one there, the same thing. This was all abrasive blasted. You can see how it's rusting back heavier down here, how it's rusting back heavier on the bottom side. Yeah, there's a little bit of rust up here on the vertical. There's probably a little bit of contamination there, but not near as heavy as it is down here. But the underside of the bottom flange is all where the salt contamination is always the worst. Salts require change. We no longer use lead. Lead paint made salts insoluble. When sodium chloride, like de-icing salts or sea salts, got on lead paint, the chloride ion likes the lead better than it likes the sodium, so it disassociated from the sodium, formed an electrochemical bond to the lead paint, and become a lead chloride. Lead chlorides are an insoluble salt. Remember I said there was a big difference. Soluble salts are hygroscopic. They draw moisture out of the air. As long as you've got air moisture available, corrosion will continue. Insoluble salts are not hygroscopic. The only time you'll have corrosion is if they're wet. If they're wet from rain or wet from the dew, if you got dew on it, corrosion will occur till the sun hits it, dries the dew up, and once the H2O evaporates, the corrosion activity stops. So lead paint saved our butt for many, many years by making an insoluble salt that didn't corrode constantly. Now that we've gotten away from lead paint, now with the coatings we're dealing with now the soluble, what starts out as a soluble salt remains a soluble salt. So the solution of one problem just caused another problem. When we got rid of lead paint, we got rid of it for a health factor. Now the result of that is it's causing another problem. Now it's causing a corrosion problem. Old habits die hard. Got a contractor who's been doing something for 20 years or 30 years. He does not want to change the way he's doing. Even spec writers, they don't want to change the spec. They want a better performance out of their coatings, but they don't they don't want to write a spec and add in salt testing because that might add cost to the job. They're not interested in increasing the cost. They're interested in increasing the performance. But unless you can find a free lunch, you're not going to increase performance without increasing cost. But people just have a hard time getting away with old habits and doing new things, especially when we talk of going from an industry that's totally visible standards to switching the industry to a non-visible. A lot of people are just dragged, kicking and screaming into it, but they are being dragged. They are having to do it. I'll preach it again. Salts are non-visible, require testing to identify. Test. Testing and limiting coating failures are always less costly than a premature failure. Testing and removal, remediation, whatever you want to call it, are always far costlier than a premature failure. Switch and go on to allowable salt levels. Right. No industry association such as NACE, SSPC, or ISO has established allowable levels. A lot of people have tried. The IMO, International Maritime Organization, they have established levels for ballast tanks of new ships only. So it's kind of a single use. Eventually, they're going to require it for ballast tanks of all ships, but it's going to be strictly on ballast tanks, nothing else. NACE document 6G186 is the only industry document that even tells you salts are bad. There's not another industry association document that even says salts are bad, let alone what to do about it. There's an awful lot of information available to the general public, good, useful information in 6G186. There's a lot of magazine articles written, but most of the trade magazine articles are more like personal opinion or personal recommendation. Most of them are not very well vetted. I've seen a lot of articles that publish stuff that just wasn't true, but according to the author's opinion, they were, but nothing necessarily meant it was or accurate. 6G186 has got a lot of information. It's the only industry document that tells you that abrasive blasting does not remove salts. I know a lot of specifiers. They've had it in their heads for years that, well, all I have to do is abrasive blast it to white metal, and that removes all the salts. So if I've truly got a white metal, I've got a salt-free surface. Well, that's BS. It just doesn't work that way. Abrasive blasting, it may reduce the salts to some amount, but it doesn't remove them. Well, we've gotten to now so many different asset owners with pipelines and with refineries and with ships and with structural steel. They've all, while the industry hasn't made up their mind what to do, they got to do something with their painting spec. They don't want to have a premature failure, so they're going in and writing their own levels all by themselves. And they're primarily being developed through individual industries, such as oil companies, the pipeline coatings, bridges with DOTs, tank linings, rail cars. The different industries are setting their own levels. What I thought was particular industry, the norms that are primarily based on what has and what has not provided adequate performance. They're not going on what works in the laboratory and what doesn't work in the laboratory. They're starting to find out what actually works and doesn't work out in the field. And which is quite good, because a lot of times what works great in the lab doesn't work worth a darn at all out in the field. But this is actual field experience of what's going on, what's working, and what doesn't work. The allowable levels that are being set by industry, and they're not exactly set, but they're being developed. I mean, they're not set that you must use them. Immersion service at ambient temperature, 3 micrograms per square centimeter for chloride, 5 micrograms for nitrate, 5 to 10 micrograms for sulfate. There's also some specifications out there, such as U.S. naval facilities, what they call NAVFAC, that are now requiring non-detectable. They started out at 3 and 5 and 10, or 3, 5, and 5, but they have found through the years that it costs just about the same amount of money to obtain non-detectable as it does to get it down to 3. If they're going to get it down to 3, they might as well get it down to 0. And for what little bit of extra cost there has been, it's really increased their performance. Some people in the power industry and tank linings and circ water pipes have said, you know, by cleaning down the non-detectable, I've greatly strung out the life of my coating systems. It's well worth doing. The other thing is increased service temperatures reduces the allowable levels. There's a JPCL article by Howard Mitschke, worked for Shell Research. If you go on Paint Square, you can research Howard Mitschke, the article, or even salt articles, and it'll come up. What he found out using a 2-coat epoxy system for tank linings at ambient service, if he had anything more than 3 micrograms per square centimeter, they failed prematurely. As soon as they got up to temperatures of, say, 120 degrees, the allowable level dropped, say, from 3 to 2. Anything over 2, they would fail. If he went up to 150 degrees, it was reduced further yet down to 1. If they had 2, it failed. By the time they got to 180 degrees Fahrenheit, if there were any salts measurable at all, they failed. They had to be down to non-detectable. Not non-detectable in a laboratory, but non-detectable with a standard field test kit. And atmospheric levels. 5 micrograms per square centimeter of chloride is the most common. Some DOTs and such are using 7. Some other specifiers are allowing 10 of chloride. 10 micrograms of nitrate and 10 micrograms of sulfate is pretty normal on bridges and structural steel. 17 micrograms is sometimes being allowed for sulfate when people are using the cleanliness levels out of the water jetting standard. There was a problem with that, and though the levels were stipulated in there under what they called SC1 or Surface Cleanliness 1, it was 0 or non-detectable. SC2 allowed 7 micrograms of chloride and 17 of sulfate. I asked Lydia Frenzel one day, the chair that chaired that document when it was written, I said, how did you ever come up with a number like 7? She said, well, we had a lot of bridge people in the room, and everybody pretty well agreed that at 10 micrograms, they were still having excessively high failure rates, but at 5 micrograms, they were having what they considered adequate performance. So the maximum allowable had to be more than 5 and less than 7, or less than 10. So we picked the arbitrary middle of 7, which was the first whole number available. Of course, they couldn't say 7.5, so they had to go either 7 or 8. So they chose 7. So I asked her, I said, so you mean 7 micrograms is as thin as ice as you can possibly ice skate on without falling through if you're really careful? And she said, yeah, that's about the size of it. I said, well, why didn't you just, if you knew 5 micrograms worked, why didn't you say five micrograms? They said, well, because some people want to be very careful to not overspecify and require too much money spent on surface prep. And I didn't say anything to her, but you know, I don't care what you spend on surface prep, it's cheaper than a coating failure. A coating failure can cost you thousands of dollars per square foot to redo. I don't know of any original surface prep that costs that much money. Anyway, if you see the number 17 micrograms per square centimeter on an atmospheric surface coating, it probably came from the water jetting spec. One other thing about the water jetting spec, in the forward, it tells you nothing in that standard should be used for anything. It's not applicable to anything other than water jetting. So if you're taking the water jetting numbers and using a dry blast job, it doesn't apply to anything but water jetting. It really shouldn't. It causes a real confusion in the job site because nobody knows whether it's right to use it or not because it tells you not to. Anyway, the numbers do vary widely as each specification is individually written and many specifiers lack knowledge about salts. So some might write real high levels, some may write real low levels, but it will change because they are individuals. None of the associations, NACE or SSPC, is going to write a standard on allowable levels anytime in the near future because there are literally hundreds of coating systems and there's literally hundreds of service environments. There's everything from 3 mil coatings to 1/4 inch coatings. There are just so many different coating systems out there and so many different uses. I don't know how they'd ever get a standard written. What does really apply, though, and it was stated by NACE in their Cost of Corrosion Survey booklet, best practices engineering will save billions of dollars. Do the best you can do in engineering it, and it will save billions of dollars. Less contamination equals better coating performance. It's that simple. Anybody has any questions, you have any comments, anything I can help you with, please feel free to email me. There's my email address, jjohnson@chlorid.com. Phone number, 800 toll-free number to our office, 800-422-3217. If you're out of area or out of the country, 480-821-0039. That ends our webinar. Hope you guys found it interesting. If you have any questions or I can help in any way, please feel free to give me a call anytime or email me. Thank you. Have a great day. Bye.